Hey guys, Mr. B here. In this video, we're going to be going over the chapter 11.3 notes, and this one is on reactions in aqueous solution. So all of these reactions are going to be taking place in water, and they're primarily going to be double replacement reactions. Okay, so we're going to be looking at the formation of precipitates, which are things that are not soluble in water, meaning they don't dissolve. So you're going to get a solid that would form in the reaction. All right, so we're going to talk about the reactions in general, as well as net ionic equations and what those are, and kind of breaking these reactions apart. So, all right, so we have what's called a complete ionic equation written here. This is a double replacement reaction between silver nitrate and sodium chloride. So I'm going to write out the regular reaction first, so you can kind of see what this reaction would look like without everything being broken apart. Okay, so we have AgNO3, which is aqueous, plus NaCl, which is also aqueous, and we're making AgCl, which is a solid, and NaNO3, which is aqueous. Okay, now real quick to make sure we understand, we can check if something is aqueous or if it's a solid by looking on the back of our periodic table at a solubility chart. So I'm going to switch to my periodic table here. And the solubility chart is this big chart here in the upper right hand corner. Okay, so this is what we're going to be using for these double replacement reactions. So I'm just write DR. So for double replacement reactions, you're always going to use this chart. Okay, and for silver nitrate, which is one of the compounds we're starting with, we can check to see if it's solid or aqueous. So we have silver here, we have nitrate here. And if we go until these things intersect with each other, we do see that it is aqueous. Okay, so that is how we know that this compound here, AgNO3, is aqueous. Same thing with this one, NaCl, that is sodium chloride. So again, we can go check on our solubility chart. We find sodium here, we find chloride here, and we can see where they intersect, and this is also aqueous. Okay, so this is how we determine if something is aqueous or solid. You're going to have to use this quite a bit and all the time when you're doing double replacement reactions, and especially for this section. Okay, so in our products, we have AgCl, and this they're saying is a solid, and then NaNO3. So this is silver chloride and sodium nitrate. So again, let's go look at those ones real quick. So let's erase these. So we have silver chloride. So silver here and chloride is here. It says solid. And then sodium nitrate. So sodium and nitrate. And this one says aqueous. Okay. So that's how we know that they're solids or not. But what we've done here in this reaction is we've taken everything that is aqueous and we've broken it apart into individual ions. Okay. So in water, an ionic compound, when it gets dissolved, the ions, which are usually bonded together when it's a solid, get kind of ripped apart. So we need to write the ions, or we can write them separately. Okay, so we see here that we have an Ag plus ion that's aqueous, plus a nitrate ion that is aqueous. So they've taken this compound, they've taken this compound here and they broke it apart into the two separate ions that make it up. Same thing with the NaCl, that's aqueous. We have a sodium ion here plus a chloride ion. Okay. On the product side, however, anything that is not aqueous would not be floating around as ions in water. It would be bonded together. So we write it as it is. So this silver chloride, which is a solid, we'll see is written here just as it is. Okay, they're not breaking the silver and the chloride apart, because in water they're not floating around as individual ions anymore, because they are bonded together in a compound that is insoluble. So it's not able to dissolve in the water. But the sodium nitrate is soluble. So we'll see that the sodium ions and the nitrate ions are again written separately. Okay, so this is what we call a complete ionic equation. It's where we take our regular reaction and we break all of the ions apart that we can, okay, that are aqueous, and anything that is not aqueous we keep together so that we can see every little piece of stuff that's like in this whole reaction. All right, so in that reaction, you might have noticed that on both sides of the equation there were some ions that were the same, okay, that didn't actually change or do anything. and we call these spectator ions. So let's go back here real quick so we can check these out. So just for 1 second, I'd like you to look at this reaction here. And I want you to tell me if you can figure out which of the ions in here are spectators, meaning they are exactly the same on both sides of the reaction and nothing changed between them. So if you take a look, we have NO3-, which is AQ, on the reactant side, and we have NO3-, that's AQ on the product side. Exactly the same, nothing changed for that. We also have Na plus AQ on the reactant side, and Na plus AQ on the product side. Again, exactly the same, nothing changed. Those ions would be considered spectator ions because nothing changed for them in the reaction. They didn't actually do anything. Okay? Before the reaction took place, they were floating around in water, and after the reaction took place, they were still floating around in water. So nothing for them happened. They would not be part of the chemical reaction. The only things that actually did anything were the silver ion and the chloride ion made a new compound that was a solid. Okay, so our net ionic equation here is where we're going to rewrite everything, but we're only going to show the particles that were directly involved in the chemical change. So I'm going to take this and I'm going to copy this over here real quick. Okay, so here's our reaction from before. And we would take this and we would erase the nitrate and the sodium. I wonder, can I... Nope, that is not what I meant to do. All right. I was seeing if I could draw on this. I probably can, but it's probably too difficult to figure out. So what we're going to do is we're going to rewrite this as a net ionic equation where we're going to have only the things that were involved in the reaction. Okay, so the net ionic equation would be Ag plus, which is aqueous, plus Cl minus, which is aqueous, and those are making AgCl, which is a solid. Okay, this would be our net ionic equation. We've removed the spectator ions, which are the nitrate and the sodiums, and we only have the Ag plus, the Cl minus, and the AgCl left, because we get rid of everything else. Okay, that's what we call a net ionic equation, and this pretty much is just specifically outlining the actual chemical reaction that's taking place in this reaction, because there's all this other stuff that's kind of irrelevant. Okay, so net ionic equation shows only the particles involved in the reaction, and it is balanced. Now granted, in this reaction everything was already balanced on its own, so you'll notice there's no coefficients here. That just happened to be the case. Okay, but we would have to still balance this reaction out, but this one just happened to already be balanced on its own. So we do still balance both sides. All right, and they show that that net ionic equation again right here. Same thing I just showed. All right, so let's take a look at our first example. So it says, in the photograph, aqueous solution of iron 3 chloride and potassium hydroxide are mixed. A precipitate of iron 3 hydroxide forms. So you can see this kind of cloudy looking stuff. That's a solid. Doesn't look like a solid because they're little particles that are all kind of evenly dispersed throughout the liquid, but it is a solid. Okay, if you waited long enough, it would settle down to the bottom as a powder. So it says, identify the spectator ions and write a balanced net ionic equation. Okay, so first we have to do a couple of things here. Okay, one, we're going to write the reaction balanced first, just regular reaction. Then we're going to write the complete ionic equation. Then we're going to write the net ionic equation. Okay, so it's going to take a little bit, but let's get started here. So complete, so let's just go, so balanced equation. Balanced, oh, what did I just do? I don't know what just happened. All right, must hit a button. Balanced equation. All right, so we're gonna have iron 3 chloride. So iron 3 chloride has a chemical formula like this. Okay, now if you are having difficulties writing chemical formulas, again, go watch videos from chapter 9 on how to do that. By this point, you should be able to write chemical formulas. So I have iron 3 chloride and potassium hydroxide, both of which are aqueous, because it says right here, aqueous solutions of these are mixed together. So we know they're aqueous. We have a precipitate of iron 3 hydroxide forming. So iron 3 hydroxide is going to be FeOH3, and it's going to be a solid because it says it's a precipitate. As for the other compound, this is going to be double replacement. So the iron is bonding with the hydroxide. Okay, that's what this product is, which means that the potassium is going to bond with the chlorine. So our other product is going to be KCl I'm going to assume this is aqueous, but we'll go check this real quick just to make sure. So let's go look on our periodic table for potassium chloride. We don't need to check the iron 3 hydroxide. It's already told us it's a precipitate. But all right, so we have potassium hydroxide. Here's potassium. Hydroxide is here. If we go until they intersect, we find that it is aqueous, which is what we figured. Usually, if one of them is going to be a solid, that means that the other one is not going to be a solid. Okay, you're never going to have two solids. So, all right, so the KCl is AQ. All right, so here's our regular equation. We have to balance this, of course. So it looks like the irons are balanced. The chlorines, we have 3 on the reactant side. We have only 1 on the product side. We're going to need to put a 3 there. That gives us also 3 potassiums now. And on the reactant side, we only have 1, so we need to put a 3 there. That will give us 3 OHs, or 3 hydroxides, but we have 3 right there. So here's our equation balanced out. Okay? So from here, we're now going to write the complete Ionic equation. So anything that is aqueous, we are going to write as separate ions. All right? So this is going to get kind of long, but we're going to do the best we can to keep it short. All right, so we have iron 3. So we have an iron 3 ion, which is aqueous. Okay, that comes from this right here. That is bonded with 3 chlorine ions. So 3 Cl minus ions that are aqueous. Now you'll notice I'm not writing the 3 as a small 3 down below. I'm writing the 3 as a big 3 out front. Okay, the small 3 down below, like it's written here, means that the chlorines are bonded together, and they're not. Once they're in water, they are separate. They're floating around individually, and there just happen to be 3 of them. So the big 3 shows that there are 3 of them, but each one is a separate individual ion. Okay, that's why I'm writing a big 3. Then we have 3 potassium ions, which are K+. Okay, those are aqueous. Okay, that comes from right here. And then we have 3 hydroxide ions as well. So 3 OH minus ions, and those are aqueous. Okay, so this is so far all of our ions on our reactant side. Okay, that's all of this stuff. On our product side now, this thing is a solid, so we will just write that exactly as it is. Okay, if it's a solid, you don't break it apart and write it as separate ions. It just stays as it is. However, this is aqueous, so we are going to write that out as separate ions. So we have 3 potassium ions, which are aqueous, plus we have 3 chloride ions, which are also aqueous. So let me make this a little bit wider so that way the Cl doesn't go down to the next line. There we go. Okay, perfect. I want it all in one line. All right. So here's everything out. If we look at it, things should be balanced, right? We have 1 iron on the left-hand side. We have 1 iron on the right. We have 3 chlorines on the left-hand side. We have 3 chlorines on the right. We have 3 potassiums on the left. We have 3 potassiums on the right. We have 3 hydroxides here. We have 3 hydroxides there. Okay, so everything should be balanced out. So that is our complete ionic equation. It says here now, we need to identify the spectator ions. So looking at this complete ionic equation, can you figure out which ions are spectators? Meaning that on the reactant side and the product side, they're both exactly the same and nothing changed for them. So if you take a look, we should see that the Cl minus ions and the K plus ions, so the 3 chloride ions and 3 potassium ions are spectators because they are the same on both sides of the reaction. So our spectator ions are the K plus ions and the Cl minus ions. If you want to put 3 and 3 to show that there's 3 of each, you can, but I'm just going to label them like that. So then finally, our last part is our net ionic equation, which is taking everything left, right, after we've gotten rid of the spectators. So we're going to have the iron 3 plus ion reacting with the 3 OH ions. Okay, so we're taking this here and this here. Okay, we're obviously not writing this and this because these are spectators. And then on the product side, these again are going to be gone, so we just have this left over. So we will have FeOH3 as a solid left over, and this is our net ionic equation. Okay, so that's basically what they wanted us to do in the problem, and I know it seems lengthy, but you know it's what they're looking for. All right, so moving on then. Again, I'm not going to be answering these questions. There's a video of me doing that. You can go watch that one afterwards if you need more help. I'm just going to be talking about the information here. So, all right, so it says, how can you predict the formation of a precipitate in a double replacement reaction? So basically this is saying, if we have a double replacement reaction, how do we know that there's going to be a solid? And this basically is going to be talking about the solubility rules and the solubility chart, which we have on the back for a periodic table. So on the back for a periodic table, we have this big chart. And anytime we have a double replacement reaction, we're going to write out the products. We're then going to check on this chart to see if any of those products are solids or aqueous or whatever. And we should be able to see that one of them is a solid. If we do one of these reactions and neither of them are solids, so both of them are aqueous, this reaction will not happen. Okay, so that means in real life, you would like pour these liquids together and then you just kind of sit there and be like, huh, well, that was boring. Yeah, nothing's going to happen. Okay, you're just going to have one container with more liquid in it rather than two containers with liquid. So you need one of these to be a solid, and if you do form a solid, then the reaction is going to happen. Okay, so we're going to use a solubility chart. They have a little smaller version of that chart right here, but use the one on the back of your periodic table. It's easier to use. Okay, so this question here says, will a precipitate form when sodium carbonate solution is mixed with barium nitrate solution? All right, so they're breaking this apart as a complete ionic equation, so you can see all the ions that are in this. So let's write what our products would be here. Okay. So let's see. We have I'm going to rewrite it as a regular equation here. So we have Na2CO3. Okay, so sodium carbonate. So right here, sodium carbonate has a chemical formula of this. So that's how I know that it's sodium carbonate, and that's aqueous, plus barium nitrate. So BaNO3 2. That's aqueous as well. So these are reactants. Okay, and again they've written them here as ions because this is a complete ionic equation, and this is going to be double replacement. So that means that the sodium is going to pair up with the nitrate, and the barium is going to pair up with the carbonate. So we're going to have NaNO3 as one product and BaCO3 as the other product. So we're going to go check on our solubility chart to see if one of these will be a solid. So let's go take a look. So we have sodium nitrate, barium carbonate. All right, so let's go see. So first one is sodium nitrate. So that's here. And that is aqueous. All right, so that one is not going to be a solid. So let's go mark that on our notes. So this is aqueous. The other one is barium carbonate. So let's go take a look at that one real quick and see if that one will maybe be a solid. So barium is here and carbonate is here, and that does say it is a solid. All right, so we will make a precipitate in this reaction. So it says, will a precipitate form? Yes. And this product here will be the precipitate. Okay, so you want to be able to write your products. And then once you have your products written, you go use that chart to figure out if one of them will be a solid. And I believe here they show this. And the net ionic equation would obviously... So let's go back real quick. Okay. Net ionic equation, if we were to write out the rest of this reaction as a complete ionic equation, the NaNO3 would be separate. And I guess it's balances too. So we need 2 there. And that is it. All right, so we would have 2 Na ions, which are aqueous, plus 2 NO3 ions, which are aqueous, plus BaCO3, which is a solid. Okay, so this little chunk right here I'm writing, this would be the second half of this complete ionic equation. I just can't fit it up on that line because this is so big. But if we notice, we'll see that we have 2 Na plus ions on the left, and we have 2 Na plus ions on the right. We have 2 NO3 minus ions on the left, and we have 2 NO3 minus ions on the right. So those are both spectator ions. So the net ionic equation would just be the CO3 2 minus plus the Ba 2 plus, and we'll make the BaCO3 solid, which then they show here as our net ionic equation. Okay, so I just wanted to make sure that you understand where this came from by looking at this part. All right, so again, There are some more questions here, but I'm not going to answer those. If you need help with those, go watch the video. But that's pretty much it for this section, okay? This section is difficult primarily because you need to be good at writing chemical formulas. If you are not good at writing ionic chemical formulas, you need to go back and practice. Otherwise, this can seem extremely hard. If you can write chemical formulas, though, no problem, and you understand how they go together with the positive ions and the negative ions, it's a piece of cake, okay? So, as always, if you need help from me, please let me know. I'm always available to help you. And other than that, I will see you in the review. All right, see you later.